So what we're going to be talking about in this video is normal forces. Basically what I'm going to be doing in the next couple of videos is I'm going to be talking about a force per video. I've already discussed weight basically in projectile motion. However, I'd rather just build upon it. Since we already know what weight is, we'll go into normal force and we'll basically add on a force, a video, and that way we start walking before we run. That way it's not like, oh, do a free body diagram right away. Like it's just. I feel like that's almost asking a little bit too much at the beginning. So let's just walk before we run. But yeah. Anyways, normal forces. So in this case, I'm going to be talking about elevators. In an elevator, you'll go up and down. I guess that's kind of obvious. But you'll accelerate up and you'll accelerate down. Which is a good problem with this. And really, that all like if you include just like your just you being in the elevator, you're gonna have a normal force going up, and then you're just going to have a weight that's pulling you down, just mg. These are the only forces acting on you. There's not like friction or anything. It's just up and down, up and down. But however, this is a dynamic problem. So just because you'll accelerate up to a higher floor or accelerate down to a lower floor. Basically with this problem, we're just going to start off, and we're going to start off doing some of the forces. So we're going to just doing the x direction, and so basically we denote that x is up in this direction. It's positive in this direction. So for accelerating down, it's going to be negative in the end. So if we do this on the forces, and like this is almost like our coordinate system, except for x is up, I guess. Doesn't really matter what we call it, x, y, z, q even. It doesn't matter. So x is just up. So if we do some of the forces in the x direction, n is pointing in the positive direction, so it's going to be n. I don't know why there's so much lag right now, but yeah. So minus mg. Then so mg is or your weight is pointing down, so then yeah, so mg is negative then. So since this is the positive direction, then we're going to say ma. So the sum of force vectors equals mass times acceleration in the end, and we're not accelerating in this direction at all, so we don't have to really essentially make it into a vector, to be honest. But yeah, so now our normal force, if we rearrange this, so add mg to the other side, is going to equal mass times acceleration plus mass times gravity. So in the end, and then n is going to equal mass times by acceleration plus gravity on the inside. So really, what is that meaning? So a lot of times when I'm like working with students, a lot of students are like, n equals mg, but in reality, this is the case some of the time. So a lot of students are like, at least how I kind of view it, at least a lot of students are like, oh well, if I'm sitting here, well then my normal force is automatically my weight, or if I'm standing here or whatnot. But in reality, we're not talking about you. We're talking about some arbitrary object, or I guess in this case, you if you're in an elevator. But it's not. This is not the case all the time. So you cannot just assume this. That's just very bad math, and then you're almost essentially just fabricating an equation out of nowhere. And what you have to do is you have to just go back to your basics. The sum of the forces equals mass times acceleration. So if the acceleration 0, then like for this case, your normal force is equal to your mass times gravity. But it's not the case all the time. So that's what trips up a lot of students. They just assume that, and they just they're like, that's that, and that's without having actually done the problem. So never assume this, and I cannot like harp that enough. That's just bad bad physics in the end. You cannot just go ahead and assume this. So, and that's mainly the whole point of this video, is you cannot do that. So, but yeah, anyways. So if we continue on with this, we have n equal to basically this, but I'm going to just rearrange this real quick. So we get gravity plus acceleration. So n is going to then equal mass times gravity plus acceleration. And so as you can see, n is just not equal to mg right away. You know, it's equal to this whole setup. It's a reactionary force, so it's more or less just a variable in there. So this is almost just like an x. So again back to n equals mg is not always the case. It's almost like assuming, like, you know, x equals 2. You know, of course x can equal 2. You know, x is a variable, but it's not always equal to 2. And like if you say this is like just automatic truth, then you're going to get it wrong. So and you know, that's like, oh, if you have 4 minus x equals 2. Well, of course this matches up with x equals 2, you know? Just like if your acceleration was 0 for right here, you know, if this guy is 0, then you get your normal force is equal to mass times gravity. But that's not always the case. Just like if 3 minus x equals 2, x is not 2. X is clearly not 2. X is equal to 1. And so more or less you get like this situation that pops up a lot. But in the end, sometimes you'll get like this situation, and that's where a lot of people get wrong answers. So again, n does not equal mg all the time. It can equal it, but you have to go out and find that yourself. So just like you can't just assume x equals 2. N equals something. It's a reactionary force, like I said. It's not something you can just say is that's that in the end. So yeah. So going on with this problem, let's just say you're going up. You know, let's just say you're going up a floor in the end. So in the end, then you're going to have a positive acceleration. So in the end, you get like. So I'm going to say n up. So that's equal to basically more than your weight, or mg. So, or I'll just call it your weight. So a lot of people just say w equals mg. I like to just write out mg right away, because this is just like another equation that you involve, you know. So, or yeah, I'll keep it right there. So anyway, so then you have your weight right here, but that's going to be greater than n equals basically when you're going down. So just because when you're going down, you're going to have a negative acceleration, you know, you're going down. So this is a negative a, really, you know, but this is a positive a. So if you have a negative acceleration, you're almost subtracting from g right here. So if g is 9.81, if your acceleration is like 3, then you know you get less than your weight in the end. So that's if you're going down. But the thing to this is that you can't go down faster than mg. You know, you can't be like if that's the case, then you would be flying somewhere up in like the middle of the elevator. You know, you would not be attached to the ground of the elevator, and that's just that would be a very dangerous elevator. You know, who want to be in an elevator where you're not attached to the floor the whole time? So essentially this has to be greater than or equal to 0. You know, you can't just no one is going to make an elevator that does that, and n can't be negative in the end. It just can't. So just because like you're not strapped into the floor, your shoes aren't just like stuck to the floor. You know, if a lot of times, you know, if you're doing a physics problem, you'll have like a guide. You know. And so essentially then you can have like a normal force that goes the opposite direction However, you have to have a guide set up. You can't just have a normal force, right? You can't have just two things contacting each other. You can't just like, have like a box on a ramp. The normal force is coming out, but like if you can't have the normal force going in to the ramp because that makes no sense. So, but anyways, so yeah, so this has to be, oh, kind of got rid of that, greater than 0. So that's just naturally if you're in an elevator. So next time you're in an elevator, you can actually think about this. So if you're this is like if you're standing still. So this guy in the end. So anyway, so n up. So this is if you have a positive acceleration. This is if you're standing still, and this is if you have a negative acceleration. So if you're standing still, n is just going to equal mg, just because this guy is 0 in the end. So really, it's just you get a g right here, and that's just weight in the end. So as you can see, if you're standing still in an elevator, if you're on the same level, your weight is equal to your normal force. But if you're going up, you're gonna basically feel the floor pushing on you a little bit more than you're normally used to. And if you're going down, then you're gonna like feel like, oh, I'm a little weightless in the end. I'm my normal force isn't as much as I'm totally used to. Of course, it's not less than your, it's not dragging you down in the end, but it's less than what you're normally used to. So, and essentially that's all I really want to talk about. So just one thing, never do this right away. Never, ever, 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 ever. I can't emphasize that enough. That's terrible. Okay. Sum of forces equals mass times acceleration.